Good morning, geometry class. Just going over the geometry lab recording sheet and assignment. We completed the front of this yesterday, and yours probably looks similar to this. If not, you might want to make it look similar to that. This part over here you can skip. This was me calculating some of the next problems. Go ahead and pause this, Tanner, if anybody is actually copying this. Otherwise, let's move on to the back side. It asks us to make a conjecture. What do you think is true about the relationship between the area and the number of lattice points on the boundary and in the interior of the figure? Write your conjecture as a formula in terms of B, the number of lattice points on the boundary, and I, the number of lattice points in the interior. So I grappled with this one and struggled with it. Hopefully I wasn't the only one. And in the end I decided to do sort of a statistical analysis of some experiments. So I first experimented with the idea of maybe the area equals or approximately equals the boundary points times the interior points. And so I plotted my solutions to B times I on this graph. So here are my solutions, and then here is the area. And if that was a good formula, of course, B times I would equal the area, and all of my points would fall on this line. So if I had a solution B times I equals 4, then my area would be 4. If I had B times I equaled 8, then my area would be 8. And as we can see, I mean, this at least would be a trend line. I'd have points kind of around it, but my trend line is nothing like that. So really, I probably could have fixed this quite a bit simply by saying B times I over 2. That might have been pretty good. I probably should recalculate based on that idea, but I didn't. I abandoned that idea and tried a different experiment. What if the area equals B plus I? So I tried that, and that was better. I mean, I'm a little off. Maybe if I would have divided that by, or multiplied it, I guess I should say, by 2/3, would that have shifted it up? I think that might have shifted it up. Looks like I need to shift it up about 1/3, right? Shift my trend line. 1/3, 1/3, 1/3. That might have been a pretty good one. But as we can see, I still would have been scattered kind of around the line. So then I decided, hey, I'm the teacher. I have the answer book. Let's look. So I looked up the answer, and here's the formula. This is Pick's formula. Whoever Pick is figured out that if you take half of your boundary points and then add them to your interior points minus 1, you oftentimes land right on that trend line. And there's a few instances where you don't. For instance, that is G and H. Where's G and H? G and H, they were pretty small, and I have a feeling it makes sense that it would sort of break down when shapes got really small. In the next, you get to kind of prove your idea about that. So I felt like if your shape got smaller, it was a lot less likely that the formula would work. So I tried some shapes for number 2, where we're supposed to test our conjecture by drawing at least 3 different figures on graph paper and finding their areas. So here are my 3 shapes. I thought this one for sure wouldn't work because, look at it's tiny. But the big one I expected to work, and it worked beautifully. The little one I didn't expect to work, but it worked beautifully. And this one, that's my shape. There's my exterior boundary. It was still pretty close. I mean, it wasn't exact. It would have been one of those points that wasn't quite on the line, but the formula gets you 22.5, and by my calculation, assuming I didn't make a mistake, which as we know is totally possible, I got 23. So if you didn't do this yet, maybe Tanner can pause the video and you can come up with some of your own ideas about that. Of course, you've seen the answer, but maybe you didn't write it down fast enough, in which case you're going to have to do a little bit of experimenting. I would love it if anybody would experiment with these ideas, b times I divided by 2, or b plus I times 2/3, but I might try that myself later. As for the rest of these questions, number 3, this is what I got. Also, just take a look at these. I don't think we really need to discuss number 3 that much. It seems to work. The formula works fairly well with a curved figure. I'm only estimating. I don't know how we can, without having a little more data, figure this area out very precisely. For number 4, I tried to use subtraction to come up with the area. I believe that is very accurate. The second part of the question is, does your formula work for figures with holes in them? And I decided it doesn't, because, I mean, I didn't figure it out yet when I wrote this, but I just thought it must not, because how do you treat these 4 points? Are they boundary points or are they interior points? So then I tried the formula out both ways with the hole as a boundary and came up with 11 boundary points and 1 interior point, and I got an area of 5.5, which is 1 off from my actual area of 6.5. And then I tried the hole as an interior and got 7 boundary points and 5 interior points, and I was off again the other direction. So I'm sticking with my no. I think it's difficult. All right. Good luck with the rest of your day. Have a great weekend.